Some of the common mistakes I saw, besides just kind of writing down like maybe a wrong cross-section formula, was not using two integrals when two integrals are needed, which is kind of like a major mistake. And then the other major mistake I saw, not too often, but being careful whether it was going to be in terms of dy or dx for the cross-section problem. Today and tomorrow, we are going to be looking at volumes of revolution. Again, it's going to be the last type of volume problem you need to know for AB calculus. And volumes of revolution, the way I think about them, is they're going to be any type of solid that can be created by rotating a region around an axis. So this is one like kind of like a woodcutting example of volume of revolution. Probably one that students have more experience with is like if anything, if you're in ceramics and have made anything on a pottery wheel, that is a volume of revolution because it's created by spinning something around. I think a really nice example to think about, especially in terms of how we approach these problems, I'm sure you've all seen like those party decorations where you open it up and it has like the tissue paper. I'm actually gonna turn on my camera because I have Miss Elsa as one, because all Party City had when I was trying to find them. But basically, we kind of think the idea is, like, if I need to find the volume of, say, her dress, I can maybe look at her dress, and, like, a part of her dress kind of looks like, I don't know, the square root function. And if I've rotated that around a region, then we do have, like, this three-dimensional figure. The important part with this three-dimensional figure, since it was created by rotating a region about the axis, the cross sections of this region are basically going to be circles, right? So they're going to be perfect circles. She's kind of beat up, but perfect circles of how it's kind of rotated around. But we can kind of imagine like any generic shape, like we have the region and rotate it about an axis. It is going to form a cross section that is circular. So basically, if you know the circle formula, the area of it, you can do these problems. Area of a circle is, of course, pi r squared. So doing a problem like this, let's do a non-calculus problem right now, just to kind of get us an idea of it. There we go. Here's a non-calculus question, but I think it helps us ease into just thinking about what these look like. So I have this rectangle, and I want to revolve this rectangle around the x-axis. So we're always going to pay attention to what we're revolving it around. It could be the x-axis, could be the y-axis, could be any horizontal or vertical line. We don't need to know how to revolve things around a diagonal, thankfully. But we're revolving this around the x-axis. So it's being spun around the x-axis. And hold on, my window is frozen on the highlighter, and I cannot deal with that. And when you revolve it, again, you don't have to imagine exactly what that region looks like, but it does help, I think, to at least have some sort of an idea. So if we're revolving this around the x-axis, what type of figure is that rectangle going to end up making? It's going to look like a cylinder, right? You can kind of imagine it. So like, I'm not the best at drawing in 3D, but this rotates around the x-axis, rotating around the x-axis. It's basically a cylinder sitting on its side. We know how to find the volume of a cylinder. So like we have that circle formula, pi r squared times the h. In this case, the radius was 3, and the height would be, is on its side, would be 2. 9 times 2 is, of course, 18 pi. Obviously, we're not going to do a question like this for calculus, but I do want to kind of talk about that answer as we get into the calculus. Pi is going to be our answer. We are spinning it around an axis, so it is going to be circular. So pi is going to be expected to be in your answer. Also, just like a cylinder, which has a base of like pi r squared, all of these three-dimensional figures will still also have a base of pi r squared. And we can even rotate it about the y-axis. So like another non-kind of calculus example. Revolving it about the y-axis, so it's spinning around this way. What shape is that still creating? Still a cylinder. And again, some people kind of visualize it a little bit better than others. There's my three-dimensional drawing. It is a cylinder. Still has like a radius. So like there is the radius. and also has a height. What will be the volume? Area of a circle is pi r squared, and the height just happens to be 3. 4 times 3 is 12 pi. Now, when we expand this into calculus, we will still be using that pi r squared. Not going to have to worry too much about the height, because that's what the integral is going to be used for. So how will these questions look in a calculus class? We're not going to be revolving a rectangle about an axis. We might be revolving something like this about an axis. So it says to revolve this shape about the x-axis. It gives you the region. So just like with all the other ones, we have this region, y is equal to that quadratic, x is equal to 1, and x is equal to 3. And we are rotating it, revolving it around the x-axis. Again, don't have to kind of visualize it. I used a computer to draw it out, and it looks something like this. So kind of like this weird, I don't know, someone in one class mentioned like they're going in like a black hole, but kind of like, you know, the cylinder starts out wide, gets narrow, and then starts getting wide again. Someone else compared it to like the sideways version of like a smokestack at like a power plant or something. I don't know, but that's basically what we're trying to find the volume of. And we're basically asked to find the volume of this, and we can find the volume basically by using that idea of volume by cross sections and just changing it up a bit. Because what are going to be the cross sections of this figure? Circles. If you're rotating it around, then all the cross sections will be a circle. Taylor?
Oh, you know those like water slides that shoot out and you go around and then you drop into the,
Yeah, it looks like that. So there's nothing.
Yeah.
So yeah, some of them will look like things you might be able to put like a name to. Some of them, honestly, that we do will just be like some completely made up 3-dimensional shape. Do want to mention that these are solid right now, like we don't have any empty space in them, so there's not going to be like empty space in these solids. This is going to be like completely solid shape that we're looking at. Yes, Hermione?
Will they always have like a normal shape cross section?
They will always be the same, and they will always be circles, because we're rotating it around an axis, so it's always going to be a circle. So if it is always going to be a circle, pretty easy to find the volume. Except now instead of cross sections, which was like you're looking at it on a bird's eye view, it's like this figure is being rotated around an axis. If we're doing a volume by cross section, I'm going to think of this as a radius instead of that b value, since we are spinning it around in a circular motion. When I draw my radius, I drew it backwards here, but I start from the axis of symmetry and then go out to the edge of the region. Since this r was going up and down, do you think it's going to be a dy problem or a dx problem? Dx, same thing we've been doing all unit long. Since it's a dx problem, is your r going to be top minus bottom or right minus left? Top minus the bottom. What's the top function? X cubed minus 3x plus 4. What's technically the bottom function? 0. X squared, not cubed. Thanks. And then we can just plug it into the volume formula. Well, again, volume is the integral of the area of a slice. What is the area of a slice? It's a circle, pi r squared. And we already said we were doing this with respect to dx. What was the r? It was the top function minus the bottom function. Again, I could have left off that 0. Make sure pi is in your answer, and then where's this integral going to start and stop at?
1 to 3.
1 to 3. Other ways you could write it, and personally how I would probably write it myself, pi is a constant, so we know that constants can be moved on the outside of the integral. So to me, it just sometimes looks less messy when it's on the outside. And then I would probably say like, hey, x squared minus 3x plus 4 minus 0. Like you can just drop off that 0 and write it like that. So that's kind of like the simplified version of that answer. If you want to think about this as a formula, which I know many of you love a good formula, so you can just kind of plug things into it. The actual name of this method is called the disk method. It's called that because the slices are circular, or they're basically forming disks. So this is going to be called the disk method. And the volume when using the disk method is the integral from A to B. If we are rotating about an axis, then we are forming circles. So we have pi r squared, and this works whether you're in dy or dx. Again, you can also write it with the pi on the outside. How do you find that expression for r? Same thing we did for the base for cross sections, top minus the bottom if you're in dx, right minus the left if you're in terms of y. Is kind of important to notice, because we won't get to it until tomorrow, but the disk method is used when you have a solid figure. So like there's no empty space when we rotate that around. So there's no like hole in the middle like a donut. So it is going to be called the disk method. Questions so far? Try this one for me then. So I have this region R, and it is, the graph is enclosed by the graphs of y is equal to 2 on the square root of 9 minus x squared, and then y is equal to 0 and y is equal to x, so just the x and y axes. Always pay attention to what you're revolving it around, that will help inform you whether it's going to be a dy or dx problem. So it says we are revolving it around the x-axis. So it's being spun around this way. Don't have to draw it three-dimensionally, but basically this is kind of like a little sideways dome type shape. What's more important though is kind of thinking about drawing in like a sample radius and using that to kind of answer your question. So if the pink stuff is too much for you, just kind of look at where I drew that sample radius and go ahead and try that one for me. And just set it up, but don't worry about evaluating. Is this going to be a dx or a dy problem? Dx, so your radius is going up and down. So we drew it from the axis to the edge of the region. I'm going to go ahead and just do it all in one step. So I have volume, the integral, and we know that this is a dx problem. This is a volume of revolution, so we have pi r squared. Pi can go inside your integral or outside your integral. I'll put it outside this time. You might have put yours on the inside. Perfectly fine. What will be the starting and ending points for this volume? 0 to 3, so using x values. And then we want to find the radius squared. Since we're doing it in terms of dx, it's going to be the top function minus the bottom function. What's the top function? 2 on the square root of 9 minus x squared minus what's technically the bottom function? 0. And we just ask to set it up. If you do have to evaluate these by hand, you often need to simplify the inside first. So maybe you like FOIL, maybe you, like this one's very easy to square everything, but it usually is just more of a tedious problem if you do have to actually evaluate it by hand. Questions on that one? All right, try this one, same region, but this time I am revolving it around the y-axis, forming I don't know what you want to call it, a little hope hat or something like that. A little hope hat. Now you're doing this one in terms of dy or dx? Dy, so you will need to take some time to put everything in terms of y. We know it's y because again, start the axis of symmetry, then go to the edge of the region. So it is going to be a dy problem. So probably the most time for this one will be solving the graph. So x equals but then basically it's just gonna be the integral of pi r squared. Yes.
Would you put plus minus for these or?
So normally when we solve a quadratic, we take the squares plus or minus. Looking at this region, I'm only on the positive side, so I can ignore the plus or minus and just use the positive one. And ultimately, it wouldn't matter, because when you're plugging it in the formula, you're squaring it. So like, even if you use the minus one, it's still forming the same solid. You're just kind of doing this side of it instead of that side, which still when you revolve it, it's still the exact same solid. So technically it doesn't matter. So this is a dy problem. So I went ahead and set it up. Again, if you see anything about revolving, go ahead and plop down a pi and plop down like something squared. You know that's going to be the format of it. Pi can go inside or outside the integral. It's dy because of the way the r is going. What numbers are going to go in your integral sign? 0 to 6. So it starts at 0, ends at 6 on the y-axis. And then define that r, we already turned to dy, so it's going to be the right function. And again, I did have to solve it for x equals the right function minus the left function, which is still technically 0. Yes?
If you left off the squared and didn't put the square root, would it be right?
So that is the integral that gives you volume. Like if you were evaluating this by hand, like sure this would become this, so like squaring that square root is just going to end up becoming like that answer. So you said you write it like that?
Yeah, would it be wrong?
It would not be wrong. It would be like if this was a free response question on the AP exam, just don't waste your time. Just leave it like that.
I mean, I would definitely write that one out.
If it was multiple choice, to be honest, I don't see them, like if it was just an equation, they would probably leave it ugly like that.
Yeah.
Just because they're testing your knowledge of like, how'd you find that R value, top minus the bottom. And often, like we're about to do the last example, oftentimes we're not going to use like the axes as like the boundary point. Like I could use a different value instead. Any other questions on that one?
Yes.
Yes, go ahead.
So there was a positive and negative finding the x.
Mm-hmm.
So you used positive.
Because I'm on the positive side, I'm in quadrant 1. Everything is positive in quadrant 1.
And then what about would you have to use the quadrant 2?
Mm-hmm. The only part that's shaded is in quadrant 1.
Oh, okay, it's shaded part. Okay.
Try this last one for me. So I have the region S enclosed by the graphs of f of x, that 20x over x squared plus 4 minus 2. And then g of x, which is just y is equal to 1, over the interval from 2 to 6. Could have taken off that part, just had you find the intersection points. I decided to make it a little bit easier by just giving you that interval. And again, all I want you to do is set up that problem of what that volume would be. Kind of, if you're trying to visualize it, it's kind of like a sideways funnel. But again, it is a solid figure, so not actually pouring any liquids down it, but funnel-ish type shape. But go ahead and see if you can write the volume of that. Again, things I can't emphasize enough, like what you're rotating it around will kind of help you draw your radius, or at least a sample radius, to help you figure out if it's going to be a dy or a dx problem. And then if you see revolve anywhere, like you know your answer has to have a pi, and you know it has to have like whatever that radius is squared. So this is actually where we'll stop at today. This one going to be a dx problem or a dy problem? Dx. And again, when I draw the radius, I start at what you're rotating it around. So it's going around that horizontal line, y is equal to 1, and then to the edge of the region. So it is being spun around that way. Actually, doesn't matter which way you spin it around, but still making that same volume. So setting it up, we said it was a dx problem. I'm not going to ask that again. What numbers are going to go on your integral sign? 2 to 6, they gave that to you. And then we know that when we rotate it around, it is circular, so stick pi on the outside of the inside. I've been putting pi on the outside, I'll put it on the inside, just this once, because again, it really is the same. And then we want to find that r value, top minus the bottom. What's that top function? 20x over x squared plus 4 minus 2, minus the bottom function, which is just 1. And then, of course, don't forget your squared, because it is based off a circle, pi r squared. Questions? Easy, easy. Where this is going to change tomorrow is we're going to talk about what happens when we revolve it, say around, if I look at this problem, maybe around the x-axis. So it'll be like a gap in the middle. So we're having going to be like fancy bun cakes or donuts, if you will. But again, it's going to be a pretty similar formula. You can just imagine it just be subtracting out the whole of the inside. But most students kind of get this pretty easily. I have had some students today finish the homework before class ended. Did want to say this about homework 3. It does ask you to evaluate the integral. Evaluate the integral if you need practice, but I'm perfectly fine if you just like set up, and leave it as is. If you finish the homework, like look over your quiz. Most of you don't have that many quiz corrections to do, if you have any of them. Looking ahead at this week, so we'll finish notes on Tuesday, and basically Wednesday and Thursday will be review days, and then your test will be Friday. Do realize there's like a lot of schedules happening this week, so like Wednesday is the Wednesday schedule, so shortened classes. Thursday and Friday will be the URL schedule, so shortened classes, but a different type of shortened class than the Wednesday schedule. So your test will be fairly short. I mean, your quiz was as well. And basically how we just changed the quiz to the test is like, instead of maybe having a problem, it's like area, cross sections, another cross section, it would be like area, cross sections, volumes of revolution. And like, pretty straightforward test, as long as you know these formulas. So yeah, y'all can go ahead and get started. Again, most of you might be able to finish that homework today. Definitely reach out to me if you have questions on your quiz.